Hi, in this module I'm going to talk about k-means, a simple algorithm for clustering, one form of unsupervised learning. So I want to start with a classical example of clustering from the NLP literature around clustering. So this was the unsupervised learning method of choice before word vectors or contextualized words, and so on. So the input to the algorithm was simply raw text, lots of words of news articles, and the output was a clustering of those words. So the algorithm was able to pick out a cluster 1, which includes Friday, Monday, Thursday, and generally days of the week. Cluster 2 had months. Cluster 3 had some sort of natural resources, and you can list. And each cluster had fairly coherent structure in it. The one thing that's quite interesting to note is that no one told this algorithm what days of the week were, or what months are, what family relations are. It was able to simply figure all of this stuff out just by looking at the data. So on a personal note, Brown clustering was actually my first experience that got me to pursue research in NLP in the first place. Just seeing the results of unsupervised learning when it worked was kind of really magical. And of course, today we're seeing even more strong evidence of the sheer potential of unsupervised learning with neural language models. So I want to contrast unsupervised learning and supervised learning. So in supervised learning, we looked at classification. You're given a training set, which is labeled. So inputs are labeled with an output Y. This goes into a learning algorithm. You get a classifier, and then you can pick on new points. And the main challenge with label data is that label data is expensive to obtain. You have to have annotated, often domain experts annotate. So in contrast, unsupervised learning, of which clustering is a form of, uses unlabeled data that's very cheap to obtain. So as a concrete example, suppose you have some points here, and they're just unlabeled points. Training data can be as here. There's points, and we want a learning algorithm that can produce not a predictor, but an assignment of each point to a cluster. I have two clusters, so let's assign the first 4 points, the blue cluster. Here are the 4 points in the blue cluster, and the second set of points to the orange cluster are the points down. So intuitively, we want to assign nearby points to the same cluster. And you can kind of see that these points are closer to each other, and these points are closer to each other, and there's some separation between clusters here. So more formally, the task of clustering is you're given some training points, dtrain, and this is a list of points, 1 through xn. And the output is an assignment of each point to a cluster. Formally, we have an assignment vector z, which is going to be z1 all the way through zn, where each zi is an element is a number between 1 and k. So assuming we have big K clusters, each point is assigned to one of the K. So what makes a cluster? The key assumption behind k-means is that each cluster can be represented faithfully by a centroid, K, and we're going to concatenate all the centroids together to form So this diagram illustrates what a centroid is trying to capture. The centroid is, in some sense, a point which is closest to all of the other points in that cluster. So represents a cluster by some concrete point in space. Centroid. So the intuition in terms of centroid is that we want each point to be close to its assigned centroid mu of zi. So a bit of notation, which I'm going to go through later. But intuitively, you can look at this point over here. We want this point to be close to the centroid of the assigned cluster, and this point close to centroid. So now we can define the k-means objective function. Here's a picture, which I'm going to talk through. So the k-means objective function is denoted as the loss, k-means loss function. And it's a function of the cluster assignments, 1 through zn, and the cluster centroids, mu1 through mu k. And this is equal to, I'm going to look at all the endpoints, sum over them, look at the ith point, look at the difference between, so zi is a number between 1 and k, which specifies which cluster point I is assigned to. And I'm going to access its centroid. And I'm going to take a difference between these two and square it. So this is the square distance between the point and its centroid. Okay, so pictorially, what I'm looking at is for each point, I look at its assigned centroid, and I'm looking at the squared of the length of these dashed lines. The sum of all the squares of the dashed lines is exactly k-mean loss. That to be as small as possible, so I want to minimize with respect to both the cluster centroids, the cluster assignments, and the centroids of this objective function. So this is, to get some intuition, let's consider a simpler example in one dimension. So here we have 4 points at 0, 2, 10, and 12. Okay, so I'm going to consider the optimistic case of if we know what the centroids are, does that make our life easier? So if we know the centroids are at 1 and 11, indeed, this becomes a pretty trivial problem because now, remember, how do we assign points? Well, for the first point, we just assign it to the closest centroid because we know where the centroids are. So this point is 0 is closest to 1, so I'm going to assign this 1. For Z2, this point is closest to 1, so I'm going to 1. This point is closest to the centroid for cluster 2, and same with this point. Okay, so all I'm doing is looking at all the centroids, and one is the closest to the point I'm trying to assign. So now let's consider the case where I don't know centroids, but I have the assignments. If I have the assignments, then I can also compute the centroids pretty. So for the first cluster, I simply look at all the points that are assigned to that cluster, and remember, I want to find the centroid, which is as close as possible to all of them on average. And so this is going to be the minimum over sum of the square distances. And recall that that is exactly optimized in closed form by setting it to the mean of the points assigned to that cluster. So for mu2, points 10 and 12 are assigned to that cluster, so the mean of those is 11. So now, given either the cluster assignments or the centroids, we can successfully recover the optimally. But this is a chicken and egg problem because we neither have the centroids nor we have the assignments to begin with. So what can we do? Well, let's just take a gamble and just initialize randomly. Okay, so we're going to initialize the centroids to some random. So usually they are assigned to some of the existing data points. So let's just assign them 0. So clearly this is not the optimum, but let's try to iterate to improve. So first iteration, what we're going to do is we're going to fix these centroids and optimize the cluster assignments. So let's look at each point and try to assign it to one of these clusters. So 0 is closest to 0, so I'm going to assign that cluster 1. This point 2 is closest to cluster 2 because it's right on top, so that's 2. And these 2 points are also closest to cluster 2. So I'm going to annotate them, assign them to cluster 2. And then I'm going to use these new assignments and try to re-estimate the centroid. So for the first cluster, I'm just going, that's only this point, so I'm going to keep the centroid there. And for the second cluster, now I have these 3 points, and I'm going to find place the centroid that minimizes the square distance to all of them, which is going to be the average at 8, which is 2 plus 10 plus 12 divided by 3. Okay, so now I have these updated centroids at 0 and 8. You can see that this is looking a bit better. And now the second iteration, I'm going to reassign the points based on these new centroids 0 and 8. So the first at this point is going to be assigned to cluster right here. This point is also going to be assigned to cluster 1 because 0 is closer to 2 than this. Point 10 is going to be closest to the second cluster, and same with point. Okay, so now we have new cluster assignments. We can go back and re-estimate the centroids. And now we're back in our familiar problem from the previous slide where we look at the first cluster, assign the centroid to be just the mean between the 2 points, and same with the second cluster, the mean 10 and 12 is 11. And now we're actually converged. If you try to repeat this process, nothing will change, so we're done. And in this case, it happens to recover the optimum clustering for these 4 points, even though we didn't know anything to start out with. So here is the k-means algorithm stated more formally. So first we are going to initialize all of the centroids randomly. Then we're going to iterate p times or until convergence. And we're going to alternate between step 1, which is set the assignments given the centroids, and step 2, which is setting the centroids given assignments. So step 1, we're going to go through each point and we're going to try to assign it. We're going to assign it to zi is going to be equal to, we're going to look at all the clusters 1 through big K. For each one of these, we're going to look at where that point is and look at the square distance between the centroid of that cluster. Squared, and then we're just going to take the argument, which is the cluster K, which minimizes this. So for step 2, we're going to loop over all the clusters, and we're going to set the centroid for that cluster to be, we're going to look at all of the points I which are assigned to that cluster, K, and just average, sum up all the points, and this will divide by the number of points I'm summing over to get the average. That equals K. Okay, so that is the k-means algorithm. So one word about whether it will work or not. So the k-means algorithm is guaranteed to converge to a local minimum of the objective k-means objective, but is not guaranteed to converge to find the global minimum. It's a cartoon picture of an optimization function. It can converge to a local minimum, but not a global. So here, if you click here, I have this demo, which shows you how k-means works. So you can actually construct your own set of training examples. And if you step through the k-means algorithm, you initialize and it alternate between moving these centroids around and reassigning the points. And in this happy case, we actually get to a pretty good clustering. The blue points over here, red points over here, and green. Training error k-means objective function is 44.7. But if I initialize in a slightly different way, so let's see what happens. It converges to something with much worse error. And you can see visually that this is a suboptimal clustering because this point has only one, this cluster only has 1 point, whereas this cluster has so many other points which are spread out. So what do you do about this? Well, there are a couple of things. One is that you can just run it multiple times from different randomizations and take the best one. Another thing you can do is use a smarter heuristic. So I didn't say very much about initialization, but there's a cool thing you can do called k-means plus plus, where you initialize the clusters one at a time, the centroids one at a time, to be the data points which are as far away as possible from all the other. So this kind of makes sure that the centroids are spread out and that they can kind of move over time to capture all of the points in your set. Okay, to wrap things up, so far we've talked about k-means, which is an algorithm for doing clustering. And clustering is a useful task that can be allowed to discover structure in unlabeled data, particular group points together. It's useful to distinguish k-means, two meanings of k-means. So the first is the k-means objective. So this is an objective function that says find assignments and find centroids that minimizes the square distance between each point and the centroid of assigned cluster. And then there's a k-means algorithm which performs alternating minimization on the k-means objective. So this is setting the assignments given the centroids and setting the centroids given the assignments. Chicken egg problem, so this is not guaranteed to globally minimize the k-means objective, although you can usually get pretty good results robustly. Stepping back a little bit, k-means is for clustering. There's other types of clustering methods out there, and clustering is a form of unsupervised learning. And generally, unsupervised learning has a few use cases. One is just data exploration and discovery. You get a pile of data, you might not have had a chance to annotate or label it. So you can run clustering or other types of unsupervised learning to group points and discover any sort of structure to get insight. And a second use case is that when you perform clustering or some sort of representation learning, you can actually get useful representations or features that you can stick them into downstream supervised learning problems when you do get a bunch of labeled data. And this generally is helpful for helping supervised learning work better. Okay, so that's the end of this module.